Hello, everyone, and welcome to the second part of the first module on Introduction to Continuum Mechanics. In this video, we're going to discuss the concept of a tensor, and in the meanwhile, we explain the difference between a tensor and a matrix. Then we discuss the tensor and vector transformations. So let's get started by the question, what is a tensor? A tensor basically is a mathematical object or structure or concept which describes a physical property and it follows certain transformation. It has a dimension and a rank. So let's break this definition into some part. So let's start with this mathematical object which explains a physical property. You may recall from your undergraduate that sigma, the stress state, is a tensor. So we called a stress tensor during the course like strength materials or physics. So we have, these components written here in this form, in this fashion. So we have x, y, and z, and here we have x, y, and z. So let's skip this follows center transformation, certain transformation, because we would like to explain it later. A tensor has a dimension and a rank, or order. We call rank order. So here the dimension are in x, y, and z. So we have 3 dimensions. So that's why we call this a 3-dimension. And it has a rank of 2. Why? Because when you want to find a component in this tensor here, so for example, sigma yz, so you have to go for the first component, which is y, which is here on the row, and then on the column, you have to find z. And the intersection of these two lines gives you the component you would like to extract. So the rank is 2. If we come to, for example, plane stress situation, when we had, for example, the plane stress situation in an XY plane, we had something like this. So the dimension is, of course, 2, and this has a rank of, again, 2. Why? Because if you want to, for example, if you want to find the component of sigma yx, so you have to go for first y, and then you go for x, and this is the component you want to extract. All right. Now let's talk about the transformation. Before transformation, I would like to draw your attention to this, let's say, to this concept of, let's say, kind of defining a tensor in another way. So suppose you have a machine, so maybe it's a good idea just y certain transformation. And you might say, why certain transformation? Because if you look at a tensor, let's suppose T is a tensor, so it acts like a black box, a machine. So this is a tensor black box. So this machine actually takes something like U and it spits out something like V, for example. So we can define a tensor as defined in terms of its actions on a vector. So to give you a better idea, we may come up with that example here. So we all know the stress state. So if you have sigma as a tensor here, or let's say this is sigma, which is a tensor, of course, stress tensor. So there is a vector like normal vector. So sigma acts on this vector and it gives, or it spits out, let's just change the direction because I may say that the direction of the initial and the input and the output vector may not be the same. That's why I draw it like this. It gives you the t, or the traction vector. And it comes actually from here that t is equal to sigma n, or maybe it's better to write it like this. Sigma n is equal to t. So so sigma acts like a transformation, a machine, or a black box, which acts on n, which is a vector, and it spits out another vector, which is not necessarily in the direction of the initial vector. I hope you got the whole idea of a tensor. So let's discuss the transformations here. Or let's say linear transformation. So if you have a tensor like T and it acts on two vectors A and B, then it should be distributable. So TA plus TB. And also if you have T alpha B should be equal to alpha TB, where alpha is a scalar. So here T it's second order tensor, or a tensor, let's say for a moment, second order. T is a second order tensor. A and B are vectors or first order tensors, and alpha is a scalar or zero order tensor. So here you might have noticed that I named this is basically a vector, and this is basically a scalar. So here you notice that I can call T as a transformation, which is a second order tensor, and I have, so it acted on A and B, and so it gets TA plus TB, so it is a linear transformation, and also acts on alpha multiply B, where B is again a vector or a first order tensor, and it gives alpha TB. So the order of multiplication is not important. We already talked about what is a tensor or a second order tensor. We call tensor, when we say tensor, okay, this is the second order tensor. And we also have third order tensors and fourth order tensors and so on and so forth. But let's have a look on the first order tensor or vector. So here, if you have a velocity vector, for example, here, so you can characterize this with v1, which is the magnitude, e1 plus v2, e2, this gives the direction, of course, plus v3, e3. So in order to characterize this vector here, you only need to know the magnitude and the direction. That's why we call it a first order. So it has, the dimension is, of course, 3 because you have x, y, and z coordinate here, and you have a rank of 1. So the order or the rank is 1 because in order to find each component, you just refer to, for example, x or y and z. So you do not have two directions. So it is not like a second order tensor. So in the case of a second order tensor, where we discussed earlier, in the case of a stress tensor, if you have an element like this is x, this is y, and this is z. So in order to find the stress component, for example, here, you may say that this is sigma yx. This is sigma xy. So the first one actually gives you the direction of the stress, which is x here on this plane, and the second component, second subscript, gives you the normal here, the normal to this plane here. So that's why we call this sigma xy. So you need two components, or the order is 2. And it is also obvious for the scalar fields, zero order tensors, where they only have a value, a magnitude, so they don't have any direction, so we call them zero order. So if you also go to my GitHub page, in the link in the description, you will see a Python script here where I brought the the concept of the generalized Hooke's law. So we start from here. The general state of stress in 3 dimension can be represented by 9 components. Yes, which are the permutations of 1, 2, and 3, or they are x, y, and z. Of directions 1, 2, and 3 are mutually perpendicular. So these these directions are perpendicular. So we have this iteration here. We imported this iterative tool here from Python, and we have all these, these permutations. So we have 1, 1, 1, 2, 1, 3. We all saw these, combinations here for x and y. So this is xx, xy, xz. This is yx. So here in the index list, I just combined these together to get, these 9 components. And finally, we have the stress. So let S be stress, and E is strain, and C is the stiffness tensor. So the generalized Hooke's law the initial and generalized Hooke's law stress-strain relation can be written as this equation here. So you'll see that here you have the stress component and the stress and the strain, which are second order because you need two directions. And here you can see that the stiffness is basically a fourth order tensor. So in order to get uh, the property you would like, you have to have three, for example, subscripts to be determined to get what you want. So the order is four. Okay, so this also gives you an idea of fourth order tensors that are available in mechanics. All right, so now let's get to the concept of tensor transformation. All right, so if you have, we already talked about this. If you have, for example, a vector here, and you want to transform it to another vector, so you use a tensor. And this is called the tensor transformation. So if you have, for example, E1, E2, and E3, and here I emphasize that we are talking about mutually perpendicular coordinate system. If they are not mutually perpendicular, it is a bit different. So you want to transform it into another, let's say, coordinate like E prime 1, E prime 2, and for example, E prime 3. So we want to know what is the transformation. So we write this transformation as this in this book, but there's also another way of writing it in some other books, but in this book we use this kind of notation. So we have our E prime 1, E prime 2, and E prime component here. And here we write our vector here, which is basically a first order tensor, as a row matrix. So we write as a tensor in a form of a matrix. Basically, the tensor and a matrix, they're completely different, but we write tensors in matrix form. And as we already mentioned, a tensor has directions. So in order to find, for example, a component here, you have to address two directions here to find your desired component. That's why we say the rank is 2. And also it follows a tensor follows a certain transformation, and it brings a physical property. So it'll talk about a physical property. So these are the difference between a tensor and a matrix. Is equal to the initial coordinate system, which is E1, E2, E3, V. Sometimes refer this to the unprimed coordinate system, and this is the primed coordinate system. And we write this as T11, T21, T31. So we fill in the rows by column, not by row. And this is T 1, 2, 2, 2, sorry, 3, 2. This is 1, 3, 2, 3, and this is T 3, 3. And if you look at the equation 2.71 in book, you will get something like e prime 1 is equal to. So I wrote this second order tensor in the form of a matrix, and the calculus of the algebra of tensor and matrix is somehow the same. They do not coincide completely, but they are somehow the same. So we can use the matrix multiplication here. So we may say that e prime 1 is equal to this row multiplied by this column. So it is t1 1 e1 plus t2 1 e2 plus t3 1 e3, and e prime 2 is this row multiplied by this. This is t1 2 e1 plus t2 2 e2 t3 2 e3, and this is e prime 3. This is this row multiplied by this column, 1 3 e1 plus t2 3 e2 plus t3 3 e3. And in book, these are already referred to t e1, so these are the transformed e1, t e2, and this is t e3. All right, so if you look at the pattern here, you will see that here you have, for example, this row, you have 1 1 1. Here you have 2 1 2 3 1 3. So this 3 3 2 2 and this 1 1 at the first part of at the first subscript of t is repeated. So we call t j e j, and this one actually appears once for each term in the expression. This is ti, and finally you have e prime I here. So I acts like a free index and j is the dummy index. Now let's get to an example to clarify things. So if you look at the example 2.73 in book, we would like to extract the suitable tensor, the proper tensor for the transformation around the z-axis or around the third axis. So let's say that you have this is E1, this is E2, and you want to transform it. You want to know how it transforms a vector, for example. It transforms in E prime 1, oh, sorry, and E prime 2 if everything is rotated around the z-axis, which is E3, and is normal to the screen. So first, we need to find the components in the previous, so we need to decompose E1, E prime 1. So if we decompose this, so it has, a projection here. So it is cosine theta, and I do not write the magnitude, which is 1, because E1 and E prime 1, they have the magnitude of 1, so I do not write it down here. And also, if we decompose this on E2, so this becomes sine theta. If we decompose E prime 2 on the E1 axis, we get something like sine theta, because this is what we want. And here is cosine theta. So if we write the transformation, we see that E prime 1 is equal to, so it has a cosine theta in the direction of E1 plus it has cosine, the sine theta, the blue one, in the E2 direction plus 0 in E3, so it didn't change. So E prime 2 is sine theta in E1, but it is in the opposite direction, so it is minus sine theta E1 plus, this is the cosine theta in E2 direction, so it is cosine theta E2 plus 0 in E3. All right. And we also have E prime 3, which is 0 in E1 plus 0 in E2 plus 1 in E3. So it didn't change. So if you write the proper transformation here, you'll see that this becomes E prime 1, E prime 2, and E prime 3 is equal to E1, E2, and E3. So I have to write these components here in the column form. So this is cosine theta. So this is sine theta. So I write these in column 0, and I write this row in column 4. Minus sine theta, cosine theta, this is 0, and this is 0, 0, and 1. And if you multiply this by this, you will get cosine theta E1, sine theta E2, 0, E3, which is the same as here. Some books also write this transformation as E prime I equal to ij ej, which does not make any difference. But we chose this kind of, notation in this book, and we follow it because of two reasons. I will explain one here in this chapter, and another in the fourth chapter when I wanna find the traction vector or the stress vector. So let's get to the next topic, which is the components of a tensor. So if you have a tensor like a tensor component like T11, we'll write it like E1 dot TE1. So this is the magnitude, and it has, one direction, and it has another direction. And you know that the dot is basically defined by the cosine between two, let's say, two directions here. And T12 is basically E1 dot TE2 here. So based on the same definition, T32 is E3 dot TE3 as 2. And generally, Tij is EI dot TEJ. And if you transform it into another coordinate, you will have something like T prime ij is equal to E prime I dot TE prime j. All right, let's get to the next topic, which is the vector transformation. Vector transformation. We already mentioned a vector like velocity vector, which is a first order tensor, written as this expression here. So if you have, for example, a vector like A, so you can write it like A E1 plus A2 E2 plus A3 E3, of course. And if you want to transform it through, let's say, a second order tensor. So you have another, let's say, vector b, which I bolded here, so show that this is a vector. T is the transformation matrix, and you have A as your, let's say, your vector here. So you will have T times A1 E1 plus A2 E2 plus A3 E3. So if you want to extract all the components of B, which are obviously 3, so we have B1, and we say, okay, this is B dot E1. Why? Because when you say that B dot E1, so we have B1 E1 plus B2 E2 plus B3 E3 dot E1 here. And here, if you expand this, so this is B1 E1 dot E1 plus B2 E2 dot E1 plus B3 E3 dot E1. This is nothing but delta 1 1, this is delta 2 1, and this is delta 3 1, which is of course 0, and this is 0, this is 1. So this will gives you P1, your desired, component. Let's get rid of these. So if you write it in this form, the dot product is commutative, so we can write this as E1 dot B1 E1 plus B2 E2 plus B3 E3, of course. So this is equal to TA, which is T here, this expression. So instead of B, I'm going to plug in this here. So we have E1 dot. So this is the same as, the bold B. All right. So this is E1 dot, and the bold B is equal to this expression here. So this is TA1 E1 plus A2 E2 plus A3 E3 is equal to E1. So I can take out A1, which is the magnitude. This is A1, E1 dot TE1 plus A2 E1 dot TE2 plus A3 E1 dot TE3. All right. So if you look at these parentheses here, you may recall these expressions here. These are nothing but A1 T11 plus A2 T12 plus A3 T13, of course. So if you do the same for B, let's say 2, you will get like A1 T1 plus A2 T22 plus A3 T23, and B3 is equal to A1 T31 plus A2 T32 plus A3 T33. So this is B1, this is B2 and B3. So if you write them down in the matrix form, we'll get something like B1, B2, and B3 is equal to, this is T11, this is T11, T12, and T13, T12 and T13 just multiplied a1, a2, and a3. And here I have t21, t22, and t23, which is a multiplication of this row with this column vector. And this row is actually the multiplication of three t31, t32, and t33 with this row here. So you may notice that this transformation, this second order tensor, is the same as what we get here. So for the sake of, continuity, we followed this notation here by writing, this transformation, this coordinate transformation like this. So basically, if you write this in the initial notation, you have bm, for example, is equal to b dot em, and this is of course this bold b here, and this bold b is nothing but t times a, which is of course let's say this is t a, the bold ones, em, and here ta, sorry, is nothing but t, and here we have ai, ei, so we can write it in this initial notation. And then we have this t, actually this can be, this is the magnitude, so we can take it out. So this is ai, this is the bold t, ei, em, and this is nothing but what we got from here, tei, which is equal to, it's better to say tei is tji ej, tji ej. So this is equal to ai tji ej dot em here, and this is nothing but delta jm. So j is equal to m to get to get this as meaningful expression. So ai t m I. So j is substituted by m, which is equal to bm. So here you have noticed that b in the matrix form, if you write this, is equal to ta. But if we have written this tei as tij ej, then we had this ai here dot em, and this gave us delta jm, which became equal to which is equal to ai tij, j is equal to m, so we may write this as ai tim, which is equal to bm. But if you compare this tim to this tmi, you see that im, they are swapped. This is basically the transpose. So if we write b is equal to t transpose a, because this is equal to tim ai, so it doesn't differentiate if you write it either way. So this becomes b is equal to t transpose a here. So for the sake of continuity, we wrote it like this, TJIEJ. We didn't follow this kind of notation, which is available in other books, for example, but some other follow this kind of notation. Uh, so in the same, when we also want to transform the normal vector in the traction vector, we have the same situation here. So we have t, which is a vector, times the stress tensor times the normal vector. We write it like this. We put all the components in a form which follows this kind of notation here, because otherwise we need to transpose it. And this actually recaps our discussion on the stress on the tensor, the second order, first order, and zero order tensor, and also the vector and tensor transformation.